7 mysteries, 1 interstellar object. 3. I/Atlas rushed in from deep space, clocking 130,000 miles per hour, and what happened next stunned NASA. No visible tail, outgassing without slowing, record-setting polarization, and a path sweeping right past Mars and Jupiter, all wrapped in secrecy. If just 2 anomalies hold up, we may be staring at a comet nobody on Earth is ready to explain. The known rules might break in the next 5 minutes, so why does 3I/Atlas look more terrifying than anyone expected? On July 1st, 2025, an alert from the Atlas Survey Telescope in Chile flagged a new object moving at extraordinary speed. Designated 3I/Atlas, it immediately stood out. Its path through the solar system was hyperbolic, confirming it as an interstellar visitor, only the 3rd ever confirmed. Early tracking pinned its velocity between 37 and 42 kilometers per second, fast enough that it would never return once it left the sun's grip. Initial size estimates ranged widely. Hubble imaging placed an upper bound on the nucleus at about 5.6 kilometers across, while ground-based observations suggested it could be as small as 320 meters. The nucleus appeared elongated, not round, with some images hinting at a stretched, possibly tumbling core. 3. I/Atlas was never a threat to Earth. Its closest approach would keep it 1.8 astronomical units away, over 270 million kilometers, well outside the orbit of Mars. Yet the timing of its arrival triggered a rare scientific opportunity. The comet would pass closest to Mars on October 3rd, 2025, then sweep near Jupiter in March 2020s before vanishing into interstellar space. Perihelion, the moment of nearest approach to the Sun, would come on October 30th, 2025, at a distance of 1.4 astronomical units, putting the object in prime position for coordinated observations across the planetary lineup. For planetary scientists, this brief window offered a chance to gather data from multiple vantage points using everything from Hubble and Webb to Mars orbiters and ground-based telescopes. The urgency was clear. 3. I/Atlas was a one-time visitor, moving too fast and on too rare a trajectory to ever be caught again. Every observation counted, because once it left, the solar system might not see another like it for decades or centuries. Outgassing is the signature move of a comet. Jets of vapor and dust erupt from the sunlit side, acting like tiny thrusters. Each burst should nudge the nucleus, causing subtle but measurable changes in its path. With 3I/Atlas, telescopes captured plenty of jet activity as it neared the sun, yet the expected recoil never appeared. Tracking teams pored over astrometric data from Hubble, the VLT, and dozens of ground stations, searching for even the faintest non-gravitational acceleration. The numbers held steady, negligible deviation, orbit solutions locked in by gravity alone. This is not how normal comets behave. Even small outbursts typically push a comet off course by meters or kilometers over time. Here, the effect was so slight that some orbital analysts began to question the mass. If the nucleus really spanned several kilometers and shrugged off jetting like a boulder ignores a garden hose, the implied mass could reach 73 trillion pounds, a figure circulating among specialists, though not yet confirmed by mainstream journals. For comparison, that's heavier than the largest known comet in our solar system by orders of magnitude. Imagine firing a CO2 extinguisher in space and watching the tank float untouched. That's the paradox at the heart of 3I/Atlas. Every jet should have left a fingerprint on its trajectory. Instead, the comet barreled on, indifferent to its own activity. The mass anomaly isn't just a curiosity, it's the first in a chain of clues that something about this visitor defies expectations. Instead of the classic bright tail slicing across the sky, 3I/Atlas presents a different spectacle. Hubble imaging reveals a luminous, diffuse envelope, an ionized shroud that wraps the comet in a soft, green haze. The usual sharp boundary between coma and tail is missing. Instead, the entire structure seems to glow, with the brightest region stretched along a single axis. This core isn't round like most cometary nuclei. It appears elongated, almost cigar-shaped, a detail that stands out even in the highest resolution frames. Astronomers note that the envelope extends much farther than expected for a typical comet of this size. Rather than a narrow stream of dust trailing behind, the material disperses evenly in all directions, forming a halo that resists the sun's push. The green hue hints at ionized gases, likely cyanogen or diatomic carbon, excited by solar radiation, but the sheer scale of the shroud remains unexplained. This morphology puzzles comet scientists. Solar system comets almost always develop a sharp sun-facing dust tail as they approach the sun. Here, the envelope stays broad and diffuse, with the elongated core riding at its center. The structure raises new questions about how light scatters through this cloud, setting the stage for the next anomaly, one that challenges even the best dust models. Light from 3I/Atlas behaves in a way that has left comet scientists scrambling for answers. When astronomers measured its polarization, the orientation of scattered sunlight, they found a record-setting negative value, -2.77% at a phase angle of just 6.4 degrees. In plain terms, this means that the light coming off the comet is polarized in the opposite direction to what's expected at that angle, and by a much greater amount than any catalogued comet, Centaur, or trans-Neptunian object. Most comets only reach negative polarization around -1.5 to -2%, and even then, only at slightly larger phase angles. The curve for 3I/Atlas is both deeper and narrower, with the inversion, the point where polarization turns positive, coming at 17 degrees, tighter than any known case. Teams using instruments like VLT's FORS-2 and the Nordic Optical Telescope's ALFOSC cross-checked their results, ruling out instrument error or calibration mistakes. The data held up, 3 independent telescopes, each confirming the same extreme negative branch. Simulations using every combination of dust size, porosity, and composition failed to reproduce the observed curve. Not even the most exotic laboratory analogs, fluffy aggregates, carbon-rich grains, or icy clusters, could match both the depth and the phase angle profile. This leaves cometary dust models at a standstill, with no known natural process able to explain such a strong and sharply defined negative polarization. The scattering behavior of 3I/Atlas's coma dust is, for now, an outlier in the solar system's catalog, a second layer of strangeness that deepens the mystery. September 2025 brought a stretch of heightened solar activity, with space weather monitors tracking a series of coronal mass ejections. Throughout this period, astronomers kept a close watch on 3I/Atlas, expecting any significant solar storm to leave a visible mark. In the past, strong CMEs have torn the tails off comets, triggered sudden brightening, or even shattered fragile nuclei. Yet, as the sun unleashed plasma and magnetic fields across the inner solar system, 3I/Atlas pressed on, untouched. No sudden outbursts, no fragmentation, and no dramatic changes in its luminous envelope were reported in the logs from Solar Orbiter, SOHO, or ground observatories. Solar physicists reviewing the event windows found no evidence of a direct hit or measurable disruption. The comet's coma stayed remarkably stable, resisting the kind of chaos that solar storms often bring. For a visitor from interstellar space, this quiet endurance stands out. The absence of any tail disconnection or rapid erosion, even during peak solar weather, reinforces the earlier hints of extraordinary mass and structural integrity. In the absence of the usual cometary drama, researchers are left with a puzzle. What kind of object shrugs off the sun's most violent outbursts without a trace? The resilience of 3I/Atlas under solar assault adds another layer to its growing list of mysteries. The orbital path of 3I/Atlas cuts almost parallel to the solar system's main stage. Its inclination, just 5 degrees off the ecliptic, puts it in rare company among known interstellar visitors. Most objects arriving from interstellar space approach at steep angles, missing the planetary plane entirely. Here, the geometry is different. 3I/Atlas will pass close to Mars in early October 2025, then sweep by Jupiter in March 2020s, tracing a line that seems almost tailored for planetary encounters. Astronomers have tried to estimate how likely this alignment is. Initial back-of-the-envelope calculations suggest that for a random interstellar object to cross within 5 degrees of the ecliptic, the odds are well below 1%. That's before factoring in the additional chance of near misses with 2 major planets in a single pass. The result is a combination so rare that some dynamicists hesitate to even assign a number without full-scale simulations. This geometry raises questions that go beyond celestial mechanics. Some in the community have floated the idea of an engineered survey path, a trajectory designed to maximize planetary flybys in one sweep. Mainstream explanations point to detection bias. Telescopes are more likely to spot objects near the ecliptic, so perhaps it's not as unlikely as it seems. Still, the alignment stands out. Whether by cosmic accident or something more deliberate, 3I/Atlas is following a route that invites scrutiny, setting up a new layer of mystery before any discussion of chemistry or missing data can even begin. Spectrographs aimed at 3I/Atlas have picked up a volatile cocktail that doesn't quite fit the usual script. The coma glows with emissions from cyanogen and carbon monoxide, 2 gases common in comets from the outer reaches of our solar system. But the proportions here are off. The CN to CO ratio, debated in late-night calibration sessions from ALMA to Mars Express, lands much closer to what scientists see high above Mars than in any Oort cloud or Kuiper belt visitor. That's a surprise. Solar system comets typically show a dominance of water and a much lower presence of these volatiles, especially so far from the Sun. Here, the CN and CO lines stand out, sometimes even outshining the water signatures, depending on the instrument and the timing of the observation. The Mars analogy keeps coming up. Some ESA teams have pointed out that the volatile inventory in 3I/Atlas's coma could almost be mistaken for a snapshot of the Martian upper atmosphere, rich in carbon compounds with a chemistry that suggests formation in a cold, carbon-heavy environment. Yet, not everyone is convinced. Instrument specialists caution that at these distances, signal-to-noise ratios are tricky and background subtraction can nudge the ratios in either direction. Still, the chemistry is hard to ignore. If these numbers hold up, they raise a bigger question. Did 3I/Atlas form in a planetary environment, or is it carrying the chemical fingerprint of a world long lost to interstellar space? The answer could weigh heavily on which hypothesis, natural, seeded, or engineered, gets the upper hand as more data arrives. During the final approach to Mars, an unusual silence settled over official data streams. For 11 days in 2025, NASA's public feeds tracking 3I/Atlas went dark. No updates appeared in the Near-Earth Object Program's logs, and the Deep Space Network's routine status bulletins offered no explanation. The timing raised eyebrows, as this blackout coincided with the comet's most favorable viewing geometry from Mars and the critical window for cross-mission imaging. Requests for internal emails and tracking logs under the Freedom of Information Act have so far yielded little, just generic shutdown notices and maintenance schedules with no direct reference to a deliberate data embargo. The vacuum of information fueled speculation. In late September, a claim surfaced online. A faint streak in a Perseverance rover navcam image, supposedly captured during the blackout, might be 3I/Atlas. The image, debated in forums and amateur circles, remains unverified by JPL or NASA archives. No official statement has confirmed or denied its authenticity, and the raw data files show no flagged anomalies. Meanwhile, rumors persist that classified radar observations, possibly from US Space Force assets, exist but remain withheld from public release. No such records have surfaced, and institutional responses have been uniformly non-committal. For comet researchers, these gaps are more than a curiosity. They highlight the tension between open science and institutional caution. When rare, high-profile objects sweep through the solar system, without transparent data, the boundary between technical delay and intentional silence blurs, leaving the scientific community and the public searching for answers in the shadows. 3 rival explanations now compete to explain 3I/Atlas. The first casts it as a rare but natural comet, shaped by the unpredictable violence of planetary systems. Supporters argue that our sample of interstellar objects is tiny, and that new arrivals may simply reveal chemistries or structures we haven't seen before. Karen Meach, a leader in interstellar comet research, urges restraint, reminding colleagues that all known comet behaviors are subject to bias and sample limits. Extraordinary claims must be matched by extraordinary, quantifiable evidence. A second, less conventional idea suggests 3I/Atlas is a planetary seed, a fragment flung from a young system carrying the raw materials for planet formation. The object's unusual chemistry and mass fuel this speculation, hinting at a deeper role in cosmic evolution. The most provocative theory comes from Avi Loeb, who argues that the object's mass, polarization, and trajectory raise the odds of artificial origin to 30 or 40%. For Loeb, the lack of a convincing natural model is itself a clue, though he concedes that without direct evidence, the claim remains unproven. With the clock ticking on 3I/Atlas's escape, the next phase is all about measurement. Teams have mapped out a clear checklist. After perihelion on October 30th, 2025, Earth-based telescopes regain their best view by December. The Hubble Space Telescope and James Webb are both scheduled for follow-up imaging and spectroscopy, targeting the comet's nucleus and coma for any late-stage surprises. The Atacama Large Millimeter Array will track gas ratios, aiming to pin down the CN and CO chemistry that's caused so much debate. Meanwhile, ESA's Mars Express and ExoMars Trace Gas Orbiter are set to sweep up data as the comet leaves Mars's orbit, offering a rare cross-check from another planet. The real wildcard comes in March 2026, when 3I/Atlas nears Jupiter. Ground-based observatories and potentially ESA's JUICE mission can look for any change in trajectory or outgassing. Each observation is a test. Does the mass anomaly hold? Does the polarization curve persist? The answers will come not from speculation, but from this coordinated campaign of eyes on the sky. The science is clear. What happens next will be decided by the data. Every anomaly in 3I/Atlas pushes the boundaries of what comet science can explain. If even a handful hold up under scrutiny, the textbooks on interstellar objects will need rewriting. The stakes reach far beyond academic curiosity. Each unexplained property, mass, polarization, trajectory, forces scientists to revisit basic assumptions about how matter travels between stars, how planetary systems form, and how rare, or common, engineered artifacts might be across the galaxy. The next wave of data could decide whether 3I/Atlas becomes a case study in natural extremes or the first credible sign of something built, not born. This is why the world's telescopes are locked on target, and why open access to every measurement matters. The outcome will shape how astronomers search for technosignatures, how agencies prioritize rapid response missions, and how the public engages with the search for life and intelligence beyond Earth. The story isn't finished. With each new observation, the question deepens: what exactly just passed through our solar system? What's clear is that 3I/Atlas challenges established comet science at every turn. Its continued observation by ALMA, Hubble, and JWST may soon decide if these anomalies point to natural extremes or something unprecedented. For now, the evidence leaves the door open.